Hi everyone, this is a brief video to show you what an isomer is. So with Lewis structures, everything often seems fairly straightforward, right? So if I have, say, CH4 methane, I know from drawing the Lewis structure, put a carbon in the center, I put my hydrogens around it, I connect everything to the carbon for a total of 8 electrons. I see this carbon has 2, 4, 6, 8, and I see each hydrogen has 2. And to verify that 8 is the total number of electrons I want to see in the drawing, I know carbon itself has 4 electrons, plus each hydrogen has 1, so that's a total of 8. So since these two numbers equal each other, we know the structure is valid. But what happens when there might be some different possibilities on how you can draw these structures? So let's look at an example of C4H10. So in the structure, if we do an electron count, each carbon has 4 electrons, and there's 4 total carbons. Each hydrogen has 1 electron, and there's 10 hydrogens. So if I add this up, 16 plus 10, we're expecting to see a total of 26 electrons. So as we often do with these carbon structures, if I put the carbons in a row, 1, 2, 3, 4, and by connecting those, I used 2, 4, 6 electrons. That leaves me with 20. Now I'm going to put the hydrogens around it, because remember, every carbon always needs 4 bonds, and every hydrogen only needs 1 bond. So if I place my hydrogens around, I use 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, which is the last that we had. So we know this structure here used a total of 26 electrons, which is what we had. All my carbons have an octet. All my hydrogens have 2 electrons for a duet, so we're good to go. But what if there's another possible structure for this? What if instead of building the carbons in a row like this, I say 1, 2, 3 carbons in a row, and I have the 4th carbon coming off the middle chain? Is this even possible? Well, let me check. So if I fill it with my hydrogens, again giving every carbon 4 bonds, every hydrogen 1 bond. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, 26 electrons. This is still a valid structure. But these two molecules themselves are actually very different from each other. This top one is something we call N-butane. This bottom one here is methylpropane. They have the same formula. Both of them are C4H10. But they're going to have different properties. They're going to have different boiling points, different melting points, different reactivities. So this happens when you have multiple compounds with the same formula, but different connectivities. These are called isomers. And when I look at connectivity, this is what I'm looking at. In this first molecule, I have 1 carbon bonded to carbon 2, bonded to carbon 3, bonded to carbon 4. Here, I have carbon 1 bonded to carbon 2, bonded to carbon 3, but carbon 4, right, instead of being attached to 3 like it is up here, it's actually attached to carbon 2. So that difference in connectivity is what makes molecules isomers of each other. So if I look at another example of this, I'm going to look at C5H12. I would at this point encourage you to pause the video to try to write at least one of these structures on your own. So the first structure that comes to mind with most people is putting all the carbons in a chain and then putting the hydrogens around them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if we do our electron counts, right, 5 carbons, each with 4 electrons, 12 hydrogens each with 1, so 20 plus 12 is going to be 32 electrons total. If I do my count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. So let's see what else we can do for connectivities of these. So for the next one, I'm going to take 4 carbons and I'm going to put a carbon off of one of these electrons, or put a 5th carbon off of one of the center carbons. So now when I place my hydrogens, right, and if you notice, the original structure we drew had all single bonds. That's a really good indicator then that any isomer is also going to have all single bonds. If the original structure you drew had 1 double bond, then everything you're going to be drawing is also going to have 1 double bond. The bonding is going to be the same, which does make it a little bit easier in terms of amounts of different types of bonds. So again, if you count it out, this also has 32 electrons. But here I have carbon 1 going to 2, going to 3, going to 4, going to 5. Here I have 1 to 2 to 3, 4, with 2 coming off to 5. Now I do want to point out that this structure is identical to if I draw it like this with my hydrogens, right? You might say, well, in this case, 5 is coming off 3, right? So shouldn't it be different? The thing is, it's not going to be different because if I took this molecule here and instead of looking at it from this side, I just turned it around and looked at it from the back side, it will be identical to that one, right? Molecules are 3D structures. You have to consider if we're looking at it from the back side, it will be the same. There is, however, one more isomer available for C5H12, and that's going to look like this. In this case, we're going to have 3 carbons in a row with carbon coming off the center and a second carbon coming off the center. So it looks like a carbon cross. Again, if you stop and count, there's still going to be 12 electrons. We're still going to have 32 bonds. In this case, I have carbon 1 connected to 2, connected to 3, 4, and 5 are coming off of 2. So that's isomers. Being able to see the isomers, being able to draw them does take practice, and it takes being able to play around and just try things and see how it works. Right? As with all of the structures, this is a little bit of art and a little bit of science. So keep an open mind, try some new ideas and structures and see how it goes. Let me know if you have any questions.